So this will be our last topic in this course that we're going to discuss, and today's topic is integration of forms. What do we mean by integration of differential forms? Let's say we have some function like this f of xy, which is a zero form, and if you want to draw a graph on the xyz axis, let's say xyz, like this, it should give you a surface area like this, a region so called. Now this region is denoted with this function, and our interest is to compute a quantity that is defined with this double integral over this region is this, something like this. We want to compute integrals that involve differential forms. So how do we proceed? Well, just like ordinary single variable or multivariable calculus, we can use the idea of Riemann summations and we can go along with it. However, if you look at this form over here, let's call it equation 1, it doesn't tell you much on how to compute or how to handle these wedge products over here, because so far we have seen that differential forms eat up vectors and we don't see any vectors over here. So we should look into another tool that will enable us to compute this type of quantities, and there is a relation. The relation is something like this. Let me first state the relation and then I'll explain what this relation means and what we are essentially doing. So instead of writing double or triple integrals, I will just use a single integral sign that can represent an n-dimensional integral, and instead of writing f of x, y, z, I will just write f, which can be a function of n variables, and then we have our differential forms like this. And this will be equal to some phi of r. That means this region is getting mapped with some mapping that is denoted with phi, and f will get mapped with phi inverse 1. This dot like thing over here is also known as a binary operation, and then there will be a pullback mapping on the differential forms. In fact, this is the tool that will enable us to compute integrals involving differential forms. Now, how does this come about? Well, the idea is as follows, is that let's say you have two copies of a same manifold. Okay, so let's say this is copy number 1 and let's say this is copy number 2. They're the same manifold. Okay, and what you are doing essentially is that let's say this manifold is endowed with a coordinate system xi's like this. Xi, that means x1, x2, x3 and so on. So when you are trying to introduce an integral that involves differential forms on manifold 1, what you do is that you want to introduce some vectors. Why? Because those vectors will make up a lattice, and on those lattice points you can define a Riemann sum and then take the continuous limit to find this relation. And when you are considering this mapping that is going from manifold 1 to manifold 2, even though they are the same, they are just endowed with two different coordinate systems, these xi coordinates will get mapped to phi of xi, or so to say phi I. And when you do that, you also have to take into account the fact that in manifold 1 there is vectors that make up your lattice points or the lattice structure, and those vectors will be pushed forward on map 2. So that's why you need to have a pullback on the differential forms that you introduce in your manifold 1. So this is one way to think of it. The proof is not very hard, but we will skip that for now, and we'll try to see how we can use this quantity. Let's say this is equation number 2, and we want to see how we can use this tool or quantity to help us evaluate different kind of integrals that involves differential forms. And before we go on, oftentimes people regard a double integral, let's say f of xy dx dy, is equivalent to a double integral f of xy wedged with dx wedged with dy. It's equivalent but not equal. The reason is the following, is that if you are familiar with Fubini's theorem, that it says that if you have a nice sort of function, then the order of the integration over here won't matter. That means if you write dx dy, the result will be the same as the following, where you interchange dy dx. But for that, this function has to have some nice sort of properties, and most of the functions will deal within this course will have that property. So from an ordinary calculus point of view, there is no difference, but in here on the right hand side we have this wedge product, right? And we know that wedge products have this antisymmetry built inside of them. There is a minus sign thing, right? So that's why when you work with differential forms, you are actually taking into account the orientation of the volume, because this quantity is actually a volume. If you want to see it, just draw the graph. This is your region f of xy, and essentially what you are doing is that this is like a height, let's say z, and this is the area that is endowed with dx dy, and you are just computing this z dx dy. So that's why we said this gives us a volume under this region f of xy. And when you are working with forms, you are also accounting for the orientation of that volume. That means whether you are working with a left-handed coordinate system or a right-handed coordinate system, and so on. So now let's try to see how we can actually use this formula to our advantage. And let's start with a very simple example. So this is our example 1. Let's say we want to compute our integral with some function f of xy, which is given as just x, right, over a region in the Cartesian manifold bounded by the lines and the reason I'm keep referring to the Cartesian manifold or Rn or R2 whatever is because things are much easier when you work with them, as the manifold itself is isomorphic to the tangent space of this manifold. So when you introduce those differential forms and vectors, you really don't have to be worried about what you are working with, whether you are working on the manifold, whether you are working on the tangent space, and so on. So this f of xy, which is equals to x, will be bounded by the lines x equals to 0, y equals to 0, and let's say y equals to x minus 2, something like this. Okay, and let's try to integrate this thing. This will look something like this, dx dy, and now we have to find out our limits. So let's say we want to integrate with respect to x first, and then we want to integrate with respect to y. So in this region you can see that if you want to integrate in terms of x first, then you have to solve for x from this equation over here, y equals to x minus 2. So this will give you x equals to y plus 2, right? Now the question is, what is the lower limit and what is the upper limit? To visualize that, you have to draw the region. So if we draw the region, it will look something like this. Okay, so from here you can see that our lower limit, where this red line is given by x equals to, sorry, y equals to x minus 2, and from this drawing or this graph over here, you can see that the lower limit would be y plus 2 and the upper limit would be 0, and then you integrate with respect to y. So what is the lowest limit of y? It's minus 2 over here, and the upper limit is 0. So minus 2 to 0. And if you compute that, what you have right now is x squared by 2, 0 to y by 2. Then you have to integrate with respect to y, and this gives you just another integral, minus 2 to 0, minus y plus 2 whole square divided by 2 dy. And the final result will be just minus 4 by 3, something like this. Okay, so this is an example of an ordinary double integral. Now what we want to do is that we want to use this idea, this one, in equation 2. So what does it tell us? It tells us that, okay, you have something like this dx1, dx2, dx3, data dxn, and now what you're doing is that you're changing your coordinate system. Why we want to do that? Well, let's say in the coordinates x1, x2, x3, the integral is pretty difficult to compute. So that's why we want to change the coordinates and we want to see what happens. So now what we can do is that we can take this integral, but now we want to change the coordinate systems. So now let's change the coordinate systems as the following way. So again, our function was what? Function was f of xy equals to x, like this, right? And let's say I want to compute that integral with the help of differential forms in a new coordinate, and the new coordinate is given by, let's say, u is equals to x plus y and v is equals to x minus y. This will be our new coordinates. Okay, so if we do that, you can immediately solve for x, which is equals to u plus v divided by 2, and y equals to u minus v divided by 2. And now we have to use the information given in the question or in the problem, is that our region was bounded by this x equals to 0, y equals to 0, and y equals to x minus 2, these three lines. So we need to translate those things in terms of the new coordinates. So x equals to 0 will give us the following, that is u is equals to minus v, that means u plus v equals to 0, right? And y equals to 0 would give us u is equals to v, and the final thing, or the final line, which is y equals to x minus 2, gives us v equals to 2. So if you draw this region in the uv coordinates, it will look something like the following. This is the u equals to v line, this one, this is u equals to v, this is u equals to minus v, which is just a mirror reflection of this guy, and then there is this v equals to 2. So this is now our new region. Okay, now what we want to do, we want to use the ideas of the differential forms, or the tools that are coming from the differential forms. And note that this change of coordinates is just that map, this phi of xy. That means this phi is taking your x and y coordinates and it's returning the new values as x plus y and x minus y, which are written as u, and v. So this is our mapping. And the phi inverse one will induce the pullback on dx wedged with dy. That means this mapping, t star phi inverse 1 dx wedged with dy, this guy. Now we have to compute the pullback, and this is pretty easy. If you just compute dx, this is what? This is just du plus dv by 2. dy will be du minus dv by 2. And if you compute dx wedged with dy, you will finally have this minus 1/2 du wedged with dv. Okay, so we computed the pullback on the forms. We computed how x and y transfers into u and v. All we gotta do right now is to just use this tool on equation 2 to find out our integration. So let's try to do that. And if you write it like this, let's say this is r tilde, where r tilde is the new region. F is now coming in terms of u and v, and the pullback gives us this minus 1/2 du wedged with dv, right? And what we can do is that we can now use this equivalence that we saw earlier. R tilde, f tilde, okay, not f tilde, sorry about that, it should be f of uv is minus 1/2 du dv. Now all you have to do is to just decide on which variable you are going to integrate first. Let's say we want to integrate over u first. We have the lower and upper limits of u, which are just minus v and plus v, and then we have to integrate over v. The values vary from 0 to 2, and you can check these things out from the above information over here. And this will be u squared by 4 uv divided by 2, like this. That means you have to put f of uv as u plus v divided by 2, then you have to integrate. If you do that, then you will have this guy over here. Okay, and finally you have to put the limits as v and minus v dv, and if you compute that, this will just be minus 1/2 0 to 2 v squared dv. This is minus 1/2, this is v cubed by 3, and finally you want to put the limits 2 and 0. So if you put 2, this is what? 2 cubed, that means 8, and there's a 2 over here, so it's minus 4 times 3, like this. Now note the fact that we took the orientation like du wedged with dv, and if we took the opposite thing, this minus sign wouldn't be here. So what would happen is that you would get a plus 4 by 3, and this is a pretty weird thing when you see it at first, because we told that this type of integrals should give you a volume, and you are having a negative sign on the volume. Again, the volume is not negative, it's just the orientation that has been changed when you went from the xy coordinates to the uv coordinates. And this is what happens with the minus sign. So when you are invoking these differential forms, you are inherently considering the orientation of your coordinates as well. So now that we have some idea on how these integrals work, let us try to go for a general kind of problems that we will see, and that is